Dear students, today we will see certain deductions of Green's theorem. These deductions are related to the flow problems. So how the Green's theorem is used for different type of situations will be discussed in this lecture. So we will go through certain deductions. The first one is that if phi and phi dash are velocity potentials, then by Green's theorem phi delta phi dash delta n ds is equal to phi dash delta phi delta n ds, or rho phi minus delta phi dash delta n ds is rho phi dash delta phi dash, this is delta phi delta n ds. So these are two deductions which we will prove by Green's theorem. Naturally we are using the Green's theorem, so all the conditions of the Green's theorem will be satisfied for phi and phi dash. What the Green's theorem says, that if phi and phi dash are scalar functions which are continuously differentiable, and delta phi and delta phi dash are also continuously differentiable, these are single valued also, then it says that a relation is true, delta phi dash is equal to minus phi dash delta n ds minus phi delta 2 phi dash ds, or you may interchange the role of phi and phi dash delta phi delta n ds minus phi dash delta 2 phi ds. So this is the Green's theorem, where naturally this is surface integral, this is not ds, this is dv, as it is the volume integral, so it is also v dv because it is also the, this is the surface integral and this is the volume integral. So these are the relations given by Green's theorem. Now under the condition of this part 1, phi and phi dash both are velocity potentials. As phi is velocity potential, this implies delta 2 phi is 0. Similarly, phi dash is also velocity potential. So this implies that delta 2 phi dash is also 0. Now using these two relations, what 3 and 4 gives, three and 4 implies the left hand side of the two are same. So the right hand side, after putting delta 2 phi dash and delta 2 phi to be 0, we get minus phi delta phi dash delta n ds is equal to minus phi dash delta phi delta n ds. Both are the surface integrals. So you may say that first part is proved. This is the first part. So removing the minus symbol, you get the first part. First part is proved. It is rather 1. So 1 is proved. Or if your fluid is homogeneous, or you can say incompressible, then you may write rho phi delta phi dash delta n ds is equal to rho phi dash delta phi delta n ds, or rho phi delta phi dash delta n ds, rho phi dash delta phi delta n ds. So you get the second part. 2 is proved. Now what is its physical interpretation? For physical interpretation, we will go to this second part. In this second part, wait for a minute. We got rho phi delta phi delta n ds. So I'll not consider this minus symbol, is equal to rho phi dash, this is phi dash, delta phi delta n ds. Now you look at the physical interpretation. In this integral, rho phi represents impulsive pressure. Impulsive pressure means a pressure which is imposed suddenly and it produces the flow with introducing this phi. That means it produces the flow, that means it introduces the velocity that is represented by phi. So impulsive pressure producing velocity, or you can say producing motion, described by phi. And what does this delta phi dash delta n represent? If I take it with the negative symbol, it represents the displacement in inward direction, and this is the displacement due to phi dash. So the combination of the two, this is the impulsive pressure and this is the displacement, the combination of the two is work. Delta phi dash delta n, if I say delta s, then it is displacement produced, provided due to phi dash. Because what is delta phi dash delta n? It is in actual the velocity. It is the velocity produced due to phi dash, and it is the component, in actual it is the component of velocity along the normal. So the combination of the two is work done by the impulsive pressure described by phi through the displacement produced by phi dash. Similarly, if I look at right hand side, in right hand side, rho phi dash, it is impulsive pressure, that is a pressure producing the sudden action, impulsive pressure producing velocity or motion described by phi dash. Yes, this motion starts from rest, and that is why it is called impulsive. It starts a sudden motion. So from rest, it is impulsive pressure. So it means it is force. Likewise, it was force. And what is delta phi delta n ds? Actually, it is for the surface delta s, and when I put the integral, it is for the whole surface. So it is displacement caused by phi, and the combination of the two again will give work done by the force or pressure described by phi dash through the displacement produced by first, that means produced by phi. So we see that we have one phi and one phi dash. Both are velocity potentials. It simply means both are representing irrotational flows. So if due to impulsive pressure, that is rho phi and rho phi dash, there is certain work done, then the work done by the first through the displacement produced by the second is equal to, you can see here, the work done by the first due to the displacement produced by second is equal to the work done by the second produced through the displacement produced by the first. So it is the physical interpretation of this deduction. Now we come to deduction 2. Now we come to deduction 2. This deduction says that if phi dash is constant, you know that there were two scalar point functions in Green's theorem. One was phi and one was phi dash. And in Green's theorem, we did not assign any characteristic to those phi and phi dash, except that those were the scalar point functions. Those were satisfying certain properties. Now, if in first deduction we have taken that suppose phi represents velocity potential, phi dash represents velocity potential. So both were potential, velocity potential functions. In deduction 2, we have taken phi dash to be constant and phi to be velocity potential. Then Green's theorem gives that, then Green's theorem shows that flow across S is 0. S means the surface is 0. Yani there is no flow, there is no flux across S. Secondly, you can say that amount of fluid inside S is preserved or is constant. If I say that there is no flow across S, it simply means I am going to prove that S is a rigid surface. Okay. So first of all, phi dash is constant, let it be K. And phi is velocity potential, implies delta 2 phi will be 0. And one another thing, since phi is constant, so what is delta phi dash delta n? ये भी कैसा हो जाएगा? This is also 0. Now, if I look at the Green's theorem, then in left hand side I was having delta phi dash. So it is left hand side of Green's theorem, and because of this delta phi dash, this also implies that delta phi dash is also 0, being constant. So left hand side of Green's theorem is 0. And in right hand side I have phi dash delta phi delta n ds plus, this was surface integral, plus phi dash delta 2 phi dv. This is the right hand side, and in this right hand side this phi dash is constant. Delta phi delta n I'll write as such, plus this delta 2 phi, because of this, is again 0. So this will be 0. So Green's theorem says k delta phi delta n ds to be 0. Now what is it? This delta phi delta n is representing the velocity along the normal, and if the velocity along the normal together through the surface ds, which is the elementary portion of S, is 0, it simply means there is no flux of fluid across S. And if there is no flux of fluid across S, the amount of fluid inside S will remain constant. If I am saying the flux of fluid, I may say that this k may be 0. I may multiply it by rho delta phi delta n ds is equal to 0. This is again representing the same thing. So deduction 2 is also complete, which says that if out of phi and phi dash, one is constant and another is representing velocity potential. What does it mean that it is representing velocity potential? It means it is representing some irrotational flow, because in case of irrotational flow only the velocity potentials exist. So velocity potential means there is some irrotational flow, and in such type of flows there will be no flow across S. So S will be treated as a rigid boundary. S is a rigid boundary. This is the meaning of no flow across S. So it is deduction 2. Now we will look at deduction 3. Next one is deduction 3. In third deduction, it is said that if phi and phi dash both become same, that is both are representing the same flow. This is number 1. Number 2, phi is velocity potential, so again it is representing irrotational flow. It is velocity potential. And third, boundaries are rigid and fixed. Boundaries are rigid and fixed. It simply means if the boundaries are rigid and fixed, that means there is no flow across boundary. Then a cyclic irrotational motion is impossible. Is impossible. In this, to derive this theorem, first phi and phi dash both are same. Second, phi is velocity potential. So if phi is velocity potential, second implies delta 2 phi is equal to 0. First implies phi and phi dash both are same. Third one is that boundaries are rigid and fixed. So we will use it later. And now see what happens. Now one another thing in this statement is a cyclic motion. A cyclic motion means that velocity potential is single valued, and we know that it is the condition of Green's theorem also. You may see that in your book, perhaps it is misprinted. There it is written cyclic motion. It is a cyclic motion. So velocity potential is single valued, which is the condition for the Green's theorem to be true. So now what the Green's theorem gives? In Green's theorem we have delta phi dash, but phi and phi dash both are same. So I may remove this dot. dv is equal to minus phi delta n ds, because I have replaced phi dash by phi, and then minus phi delta 2, again phi dash is replaced by phi ds. Oh sorry, this is dv, this is the volume integral, this is dv, but delta 2 phi is 0, so it will disappear and we are left with phi delta n ds, and left hand side will be written as delta phi square. Now what is delta phi square? It is in actual delta phi delta x square plus delta phi delta y square delta phi delta, if you are working in 3-dimensional motion, z square dv minus phi delta n ds. And I may write it as, this is q square, if q is the resultant velocity. So it is q square dv is minus phi delta n ds. Now at this stage also I may say that I have proved the theorem, but I'll convert it into an expression in terms of kinetic energy, and then I'll say you that how we are getting the proof of this theorem. I got q square dv is equal to minus phi delta n ds. So what I do, for incompressible fluid, I may write rho q square dv is minus rho phi delta n half of ds, or I may write it as rho phi minus half of delta n ds. Now what is this expression? This is kinetic energy. kinetic energy. Let I denote it by T. Kinetic energy T is equal to rho phi minus half of delta phi delta n ds. As I told you earlier, this delta phi is impulsive pressure. Okay. And what is this? This is half of velocity along normal, and this is with minus symbol, so it is representing the half of velocity along normal in inside direction. At that point. Now this point is arbitrary and this is on the surface ds. So it is true for all the points on the surface. So what is the final kinetic energy? It is the sum of all the products, sum of the product of each impulse and half of the velocity at that point where the impulse is applied. And so this shows that this kinetic energy is depending upon the boundary. Whatever is the motion of the boundary or whatever is the flux through the boundary is the main factor on which this T is depending, because T is the sum of all the impulses applied on any point, arbitrary point of that surface ds, and producing and it is expressed in terms of impulsive pressure, product of impulsive pressure with half of the velocity at that point. So it simply means that T is depending upon the motion of the boundary. Now your boundary is rigid. So what is delta phi delta n? Whatever is it, either I take it with positive symbol or with negative symbol. What is delta phi delta n? This will be 0 if your boundary is fixed and rigid. And so 3 implies T is equal to 0, which implies half of rho q square dv is equal to 0, or I may use the previous relation, second relation. Then in that case I have not to write T is equal to 0, rather I'll use that relation. I am not using this relation. This relation is derived just to show that kinetic energy is depending upon the boundaries, and your boundaries are rigid and fixed, and because the boundaries are rigid and fixed, delta phi delta n will be 0. And from the previous derivation you will get, previous page, you will get q square dv is equal to 0. This is positive, being square of q, and dv is arbitrary. So what the integral q square dv is equal to 0 imply? That q square is necessarily 0 or q is necessarily 0. And because q is 0, this implies there is no motion in fluid. So what was the corollary? It was saying that a cyclic irrotational motion is impossible. The motion is acyclic because we have used the Green's theorem, and it is the condition of the Green's theorem that your phi should be single valued. So your motion is acyclic. Secondly, phi was representing velocity potential. So motion is irrotational as well. So what we got, that a cyclic irrotational motion is impossible. The one thing which you have to keep in mind is that to come to this result, a cyclic irrotational motion is impossible, we have used a volume which is bounded by a surface S. So we are deriving this theorem in the reference of a surface bounding a region containing a fluid. Okay, because in next lecture I'll tell you something about a motion in which we will talk about some common region between the two boundaries. So now this deduction is completed, and these are the three deductions which we derived with the help of Green's theorem. And here one more thing is that we also know that your kinetic energy is defined in this way. Kinetic energy is equal to rho phi minus half of delta phi delta and ds, which we will also use later. And now we will define the kinetic energy when your fluid is confined between two boundaries, because in this case your fluid is not confined between two boundaries, rather it is enclosed within a boundary which is having the surface S and the volume V. So come to next part, which is the kinetic energy of infinite liquid. Actually, that was not the kinetic energy for infinite liquid. Whatever we did in previous part was kinetic energy when your fluid has some surface S bounding a volume V. Now it is kinetic energy of infinite liquid. That means we have to consider infinite mass of liquid. And motion is irrotational. Naturally, motion is irrotational because you have to consider the velocity potential. Fluid is incompressible. And fluid is at rest at infinity. Further, this is important point, flow region is bounded internally by a solid boundary. You know what is the meaning of solid boundary? That simply means there is no flux across this boundary. The second important thing is that your fluid region is bounded internally by the solid boundary, say S, and externally by a large boundary S dash. Now here another additional thing is that your fluid is externally bounded by a large boundary, and you have to consider the infinite mass of liquid. So in the process we will take this S dash to be very large, extending to infinity. So it is a large boundary S dash. Then T is defined as minus rho by 2 phi delta phi delta n ds. You may think that it is the same expression as I got in previous part, but now the conditions are different in this part. You are talking about an infinite mass of liquid. So the first thing is, this is not the proof actually, this is just a derivation of this expression. The first thing is that motion is irrotational. So I'll give here numbers 1, 2, 3 at rest at infinity, and region is bounded by these two boundaries. So first implies infinite mass of liquid. I am writing the second one. Second implies there exists some velocity potential, because your flow is rotational. So some velocity potential, say phi, such that delta 2 phi is equal to 0, and phi is single valued naturally. Now let us assume that phi and phi dash are same in Green's theorem. It simply means that there exists one type of a rotational motion. So phi and phi dash are same. Then what we get? Then from Green's theorem, delta phi dv is equal to minus phi delta n ds, because I have taken phi and phi dash to be same. Or this implies, again I may write it as q square dv is equal to minus phi delta n ds, or rho by 2, I am multiplying both sides by rho by 2, q square dv is equal to minus rho by 2 phi delta n ds. Now this is naturally kinetic energy. T is equal to minus half of rho phi delta n ds. Naturally this is the surface integral bounding a fluid region. Now this is the kinetic energy for the surface S. Now what will be the kinetic energy for the surface S dash? That will be, for surface S dash, we will have T is equal to minus half of rho phi delta n ds for S dash. I think that was 5. So it is 6. Now what is kinetic energy bounded by the region S and S dash? It will be half of rho phi delta n ds for the surface S, half of rho phi delta n ds for the surface S dash. Now we will use equation of continuity. This is your surface S and this is your surface S dash. This is S and this is S dash. Equation of continuity says that whatever liquid is entering through this should be same whatever liquid is going out from S dash. Now what will be liquid? Yeah, amount of liquid or flux of liquid through S. It will be rho delta n ds, density into velocity. And what does this minus delta n is representing? If I am taking this direction, So is it the inward direction or the outward direction? This is the outward direction for this surface, and this is the outward direction for this surface. So it is in the inward direction, and that is why minus symbol is representing the flux of liquid through S. Okay. And what is the flux of liquid through S dash? For S dash, this is the flux of liquid. This is the outward flux of liquid through S dash. It is outward. It will be with positive symbol, rho S dash delta phi delta n ds. And what the continuity equation says, or what the mass conservation law says, that the two should be same. So by mass conservation law, minus rho delta phi delta n ds for the surface S should be equal to rho delta phi delta n ds, or I may write S delta phi delta n ds plus rho S dash delta phi delta n ds, say P 10. Now from the expression of T, I am using the two expressions, and the previous expression will be multiplied by C by 2. You look at the two expressions. This is expression 7 and this is expression 10. Oh, here I have to write it as equal to 0. I'll operate C by 2 here. I operate C because I have to combine it by this. So I have to operate C by 2 on 10, and then I'll subtract the 2. So T will remain same because it is equal to 0, and these two will be combined. So I may write T is equal to minus rho by 2 phi minus C delta phi delta n ds minus rho by 2 phi minus C delta phi delta n ds for S dash, and this is for S. Now it is said that your internal boundary was solid. So this simply means that there is no flux across that. So what will happen? That delta phi delta n ds will be 0 for the surface S. No flow across S being solid. Further, if delta phi delta n ds is equal to 0, then from your relation which we write because of equation of continuity, delta phi delta n ds for S dash will also be 0. This implies rho delta phi delta n ds S dash is again 0, or rho delta phi delta n ds for S dash 0. What does it show? It shows that this is independent of boundary. This is independent of boundary S dash. Implies rho delta phi delta n ds for S dash is independent of boundary. Because it is true for S, it is true for S dash. S dash is infinitely large and it is arbitrary, so it is independent of boundary S dash. boundary means boundary surface. Boundary surface S dash. So what does this relation imply? A implies T is equal to minus half of rho phi minus C delta phi delta n ds, because this part will be 0 when I say that phi tends to C. If phi tends to C, this will be 0 because of this relation. Or minus half of rho phi delta n ds plus C rho by 2 delta phi delta n ds is equal to kinetic energy T. But this is again 0. So T is equal to minus half of rho phi delta n ds. So it is the expression for the kinetic energy. Here when I say that phi tends to C and S dash is enlarged infinitely. This was the larger surface. Now you have extended it in all directions. So in that case, this will be your kinetic energy. So this is all about the deductions and the kinetic energy. This is the kinetic energy of the liquid extending to infinity. This is all about this lecture.